Let us talk about variational principle. Of course, it's an approximation that's being exploited to solve some of the problems in quantum mechanics. This variational principle is basically it's a method that's useful for determining the eigen energies or eigenvalues and the eigenstates. So this variational principle can be utilized for determining these eigenvalues and eigenstates of a system whose Hamiltonian is known. So the Hamiltonian is known. And this Hamiltonian cannot be exactly, or by some perturbative treatment, cannot be exactly solved. Therefore, it's particularly, useful for determining the ground state of quantum systems. Now, for a system described by the Hamiltonian, the ground state energy is calculated via this variational principle without actually solving the Schrödinger, without actually solving the Schrödinger's wave equation. And according to this principle, the ground state energy, so if I assume that Eg is ground state energy, then in view of this principle, the ground state energy of the system is simply the expectation value of Hamiltonian, and in a normalized state. So I can say that this, if I have to calculate the expectation value, say psi, h cap, and psi, this psi is normalized. So in view of variational principle, the ground state energy that's calculated is either less or equal to this expectation value, psi h psi. And this can be written as h cap, the expectation value of the Hamiltonian. In actuality, we have it divided by psi and psi, since the wave function is normalized. That's why its value is equal to 1. Now, there can be a state. In the ground state, the energy Eg, that's our ground state energy. But if the state psi is excited, now if it is excited, if it is in the excited state, then the expectation value, that is this psi h psi, this expectation value, it will exceed this ground state energy. Means it will be greater than that of the ground state energy of the system. So if we take, say for example, let me choose a trial wave function, assuming the trial wave function, let us assume that this trial wave function is psi, and this trial wave function is assumed to be the linear combination of different exact eigenstates of the Hamiltonian operator. So if I write down this state as the linear combination of different eigen states of H. So I can write down this as sigma n Cn, then say phi n. Now, this Cn is the coefficient of all different states that have been considered. Now, if I take its complex conjugate, so this ket will transform into the bra, so we will have sigma n Cn star, and we will have bra of phi n. All right, so as we know that this wave function is normalized, and if the wave function is normalized, then the condition that psi and psi is equal to 1 should hold, and the condition phi n and phi n equal to 1 should hold. So if that's the case, and if I write down this state as psi and psi, this will be equal to sigma n, then Cn star, then phi n and phi n. But this is equal to 1, and this is equal to 1. So this is 1, and this is also 1. So I'll say that sigma n Cn star is equal to 1. And from here, we have Cn and its star, and that's going to give me the Cn scar. Sigma n is equal to 1. So what does that mean? That means this Cn that we have, this Cn is, the magnitude of this Cn is equal to 1. Now the expectation value. Now I would like to calculate the expectation value of the Hamiltonian. So how to calculate that? So the expectation value of Hamiltonian will be simply psi h cap psi, and this must be equal to sigma n and sigma n, and then Cn star, then you'll have Cn, then you'll have phi n and phi n. Oh, sorry, there has to have the Hamiltonian, so h phi n. All right, so we can write down here, this is sigma n, this is C n square, and if we have phi n of h, this is going to give us phi n of En. So this is Schrodinger's equation. Okay, so in the Brown notation, and so for this phi n h, I can have phi n, then phi n, and since En is the energy eigenvalue, it's a constant, it will come out, so this is En. So the expectation value of the Hamiltonian will be sigma n Cn square, and phi n will be equal to 1, and then En. But we have already calculated the magnitude of this Cn square equal to 1, so the expectation value of this Hamiltonian is simply equal to En. So as per the given condition, if we are talking about the ground state, and this ground state is the smallest eigenvalue, so I should say that this Eg, the ground state energy, it should be less or equal to the expectation value of this Hamiltonian, and this is equal to En. Now this is the result that we were interested in. Now, what happens in general, in general, to calculate the ground state and the ground state energy, we have to make a calculated guess. Basically, I should call it calculated guess of this trial wave function. and and this trial wave function, it contains all the physical properties of the ground state. It contains the symmetries, it contains the smoothness, all of the things, all the information is accounted in this trial wave function in terms of some variable parameters. Variable parameters. And what could be those variable parameters? It could be anything, say zeta 1, zeta 2, and so on and so forth. And we can have a state of vector, say psi, and this psi can be the function of these parameters: zeta 1, zeta 2, zeta 3, and so on and so forth. Then we should be searching for the minimum value of this expectation value of this Hamiltonian by varying these adjustable zetas, and so that one can one gets the closest estimated possible eigenstate and eigenenergy for this selected trial wave function. Now, for example, if we talk about calculating the ground state of hydrogen atom, and we have the best trial wave function for that, psi equal to e to the power of minus alpha x, where this alpha is that variable parameter that needs to be adjusted with respect to the particular problem. So with this, I would like to stop here. Okay, goodbye.